Long before concrete walls rose across canyons, before transmission lines stretched across deserts, and before vast cities shimmered beneath desert sunlight, a river was already shaping the destiny of an enormous region of North America. The Colorado River begins as a gathering of mountain waters. High among the snow-covered peaks of the Rocky Mountains, winter storms deposit layer upon layer of snow. For months, the frozen accumulation remains locked in place. Then spring arrives. Temperatures rise, snowfields begin to soften. Tiny streams emerge from beneath drifts and flow downhill through valleys carved over countless ages. Each trickle joins another. Creeks become streams. Streams become rivers. Eventually, those waters unite into one of the most influential waterways on the continent. The Colorado River travels approximately 1,450 miles, or about 2,330 kilometers, from its headwaters to the Gulf of California. Along that journey, it cuts through mountains, plateaus, deserts, and canyons. It crosses landscapes so dramatically different that they appear to belong to separate worlds. For thousands of years, the river existed according to rhythms established long before human memory. Snowmelt from distant mountains would surge southward each spring. Seasonal floods spread across valleys and floodplains. Sediment carried from far upstream settled onto fertile ground. New channels formed while old ones disappeared. Entire sections of river shifted position over generations. To modern observers, accustomed to maps and boundaries, such behavior might seem chaotic. To nature, it was simply normal. The river's annual floods created corridors of life across regions that otherwise received very little rainfall. Cottonwood forests flourished along riverbanks. Wetlands emerged where floodwaters lingered. Fish adapted to the changing currents. Birds followed migration routes linked to the river's resources. Human communities followed as well. Long before modern states appeared on maps, indigenous peoples learned to live alongside the Colorado River and its tributaries. Their knowledge developed over centuries of observation. They understood the timing of floods, the behavior of seasonal waters, and the opportunities hidden within an environment many outsiders would later dismiss as harsh and unforgiving. Along portions of the river, communities practiced sophisticated agriculture. Fields of maize, beans, squash, and other crops benefited from fertile soils enriched by flood deposits. Irrigation channels directed water where it was needed. Settlements emerged in places where the river provided stability in an otherwise unpredictable environment. The relationship was not one of conquest, it was one of adaptation. The river could nourish communities, but it demanded respect. Floods could replenish fields one year and destroy them the next. Channels shifted, water levels changed. Survival depended upon understanding those patterns rather than attempting to overpower them. Centuries later, explorers from Europe entered the region and encountered landscapes unlike anything they had known. Many viewed the Southwest through the lens of scarcity. Rainfall was limited. Summers were intense. Vast distances separated settlements. Yet beneath that apparent scarcity flowed a remarkable source of wealth, the Colorado River. As territories expanded and populations increased, attention increasingly focused on its potential. Farmers recognized opportunities for irrigation. Entrepreneurs imagined transportation routes and economic development. Political leaders saw possibilities for growth on a scale previously unimaginable. The challenge was that the river refused to remain predictable. During some years, abundant snowpack produced powerful flows. During others, runoff declined. Floodwaters occasionally surged with tremendous force, sweeping away infrastructure and reshaping landscapes. Communities that relied upon the river benefited from its generosity, but they also lived with uncertainty. Throughout the 19th century, settlement accelerated across the American West. New towns appeared. Railroads connected distant regions. Agricultural development expanded into areas once considered marginal for cultivation. Again and again, planners returned to the same realization. The future of the Southwest depended on water. And much of that future depended specifically on the Colorado River. As irrigation networks expanded, farmers transformed arid valleys into productive agricultural regions. Crops flourished where desert conditions had once dominated. Economic opportunities multiplied. More settlers arrived. Each new success increased demand. Each new demand increased pressure. The river that had sustained ecosystems and indigenous communities for millennia was now expected to support rapidly growing populations, expanding agriculture, industrial development, and future cities that had not yet been built. Yet the river itself remained unchanged in one important respect. It still followed its own rules. Spring floods continued. Seasonal variability continued. Years of abundance alternated with years of scarcity. No matter how ambitious human plans became, the Colorado River remained a force shaped by geography, climate, and time. By the early decades of the 20th century, leaders across the Southwest increasingly reached the same conclusion. The river represented extraordinary opportunity, but opportunity alone was not enough. Water arriving at the wrong time could be almost as problematic as water that never arrived at all. Floods damaged communities. Seasonal fluctuations complicated planning. Disputes emerged over who possessed rights to use the river's flow. The river offered prosperity. The river also offered uncertainty. And uncertainty was becoming increasingly difficult for a growing region to accept. The challenge was never finding value in the Colorado River. The challenge was controlling it. The desire to control the Colorado River did not emerge from ambition alone. It emerged from necessity. Across the American Southwest, communities were discovering that prosperity and uncertainty often arrived together. The same river that nourished farms and supplied growing settlements could also unleash destructive floods. Entire seasons of planning could be overturned by a single powerful surge of water moving downstream from distant mountains. In spring, melting snow from the Rocky Mountains often produced tremendous flows. Water rushed through narrow canyons and broad valleys alike, carrying sediment, debris, and immense energy. During especially wet years, the river expanded beyond its banks and spread across floodplains that had been shaped by thousands of years of similar events. For centuries, nature accommodated these cycles. Human infrastructure did not. Railroad crossings, irrigation systems, roads, canals and settlements were far less adaptable than the ecosystems that had evolved alongside the river. Every flood brought financial losses. Every damaged canal disrupted agriculture. Every unexpected surge reminded planners that the Colorado River remained largely beyond their control. At the same time, another challenge was becoming impossible to ignore. The Southwest was growing. New residents arrived seeking opportunities in agriculture, mining, transportation, and commerce. Cities expanded. Demand for reliable water supplies increased. Farmers wanted assurance that irrigation water would remain available during dry years. Municipal leaders sought confidence that future growth would not be limited by unpredictable river conditions. The Colorado River represented a solution, Yet it also represented a problem. Water flowed through the basin according to nature's schedule rather than humanity's needs. Enormous quantities might pass downstream during one season only to become unavailable during another. Without large-scale storage, much of the river's abundance effectively disappeared into the distance before it could be captured and used. The idea of storing water was not new. Civilizations around the world had constructed reservoirs and irrigation systems for thousands of years. What made the Colorado River different was scale. Everything about the river basin seemed immense. The distances were immense, the canyons were immense, the seasonal flows were immense. Any effort to regulate such a river would require engineering on a scale rarely attempted before. By the opening years of the 20th century, engineers began examining possibilities. Surveys explored locations where dams might capture and store vast quantities of water. Geologists studied canyon walls. Hydrologists analyzed river flows. Government officials debated costs, benefits, and risks. Among the locations attracting attention was a dramatic section of the river where steep canyon walls narrowed the channel into a natural bottleneck. The geography seemed almost designed for a massive structure. Yet transforming that possibility into reality would prove extraordinarily complicated. Water disputes had already begun to emerge between states sharing the Colorado River basin. Communities upstream and downstream viewed the river through different priorities. Agricultural regions sought dependable irrigation supplies. Growing urban centers anticipated future demand. Each state feared that others might claim more than their share. Negotiations became increasingly urgent. Without agreements governing water allocation, large infrastructure projects faced political obstacles as formidable as any engineering challenge. The debates eventually culminated in efforts to divide the river's waters among basin states. Representatives gathered to discuss rights, responsibilities, and expectations for the future. Their decisions would shape development across the Southwest for generations. At the time, optimism was widespread. The prevailing belief held that engineering, planning, and infrastructure could overcome nearly any obstacle. Across the nation, railroads crossed mountains, bridges spanned enormous rivers, and new technologies transformed daily life. Confidence in human ingenuity was high. Many viewed the Colorado River as another challenge awaiting a solution. The river flooded. Build a dam. The river varied from season to season. Store water. The river created uncertainty. Regulate its flow. The logic appeared straightforward. As studies continued, support for a massive dam gradually strengthened. Advocates argued that such a structure could provide flood control, water storage, irrigation benefits, and hydroelectric power. Instead of allowing seasonal surges to pass unused downstream, a reservoir could capture that water and release it when needed. The concept promised stability. For farmers, it promised reliable irrigation. For cities, it promised dependable water supplies. For industries, it promised electricity. For governments, it promised economic development across a vast region. The vision was breathtaking in scale. Engineers imagined a structure taller than any dam previously built. They envisioned a reservoir capable of storing years of river flow. They proposed generating electricity from the river itself, transforming falling water into a source of power for communities hundreds of miles away or hundreds of kilometers away. Such ambitions inspired excitement. They also inspired skepticism. Many questioned whether a project of such magnitude could actually be constructed. The proposed location lay within a rugged desert environment where summer temperatures regularly climbed to punishing levels. Transporting equipment, materials and workers into the canyon would be difficult. Diverting an entire river during construction seemed almost unimaginable. Yet the idea continued gaining momentum. Each year brought additional studies. Each study strengthened confidence. Each discussion moved the dream closer to reality. Then larger historical forces accelerated the process. Economic uncertainty spread across the United States. Communities searched for projects capable of creating jobs and stimulating growth. Large public works increasingly appeared attractive, not only as infrastructure investments, but also as economic lifelines. The Colorado River project suddenly represented more than water management. It represented hope. It represented employment. It represented a vision of the future at a moment when many Americans desperately needed one. Plans evolved from concepts into blueprints. Blueprints evolved into commitments. Commitments evolved into action. Far from the growing cities that would eventually depend upon it, a remote canyon awaited transformation. There, amid towering walls of rock carved by geological forces over millions of years, engineers prepared to attempt something unprecedented. The answer would arrive in Black Canyon. Black Canyon did not appear to be a place where one of the greatest engineering achievements in human history would emerge. The landscape was severe, immense, and unforgiving. Towering canyon walls rose above the Colorado River like stone fortresses sculpted by time itself. Summer temperatures frequently climbed beyond 120 degrees Fahrenheit, or approximately 49 degrees Celsius. Rainfall was scarce. Vegetation was limited. For much of the year, the environment seemed almost hostile to large-scale human activity. Yet it was precisely this dramatic geography that attracted engineers. The canyon's narrow width and strong bedrock offered an opportunity unlike any other along the river. If a dam could be anchored between these massive walls, it might hold back an extraordinary volume of water. The challenge was turning that possibility into reality. Before construction could begin, workers faced a problem so fundamental that it bordered on the impossible. A dam cannot be built in the middle of a flowing river. The Colorado River first had to be moved. Engineers devised a solution that sounded almost unbelievable. They would carve enormous diversion tunnels through the canyon walls themselves. Instead of allowing the river to continue along its natural course, they would temporarily redirect it through these artificial passages. The scale of the undertaking was staggering. 4 massive tunnels were planned, 2 on the Nevada side of the canyon and 2 on the Arizona side. Each tunnel would measure approximately 56 feet in diameter, or about 17 meters in diameter, large enough to accommodate a substantial building. Creating them required workers to blast, drill and excavate millions of cubic feet or millions of cubic meters of rock. Day after day, crews descended into dangerous conditions. Pneumatic drills hammered relentlessly into stone. Explosives shattered canyon walls. Dust filled the air. Temperatures inside the tunnels often reached extreme levels, creating working conditions that tested human endurance. The hazards were constant. Falling rock threatened workers from above. Machinery accidents occurred without warning. Heat exhaustion remained a daily concern. Despite these dangers, progress continued. Thousands of men arrived seeking employment during the depths of the Great Depression. Across the United States, economic hardship had left millions unemployed. Families struggled to survive. For many, a job at the dam represented an opportunity that could not be ignored, regardless of the risks. Workers travelled from distant states carrying hopes of steady wages and a better future. What they encountered was a construction project unlike anything most had ever seen. Temporary camps emerged near the canyon. Roads were built. Supply chains were established. Equipment arrived in vast quantities. Engineers, surveyors, geologists and labourers worked together in an environment where every task seemed larger than life. As excavation advanced, another challenge became apparent. The canyon walls themselves required preparation. Loose rock had to be removed before concrete placement could begin. High scalers, as they became known, descended on ropes from towering cliffs, dangling hundreds of feet or dozens of meters above the river below. Armed with jackhammers and small explosive charges, they chipped away unstable rock that might otherwise threaten the structure. The work demanded extraordinary courage. One misplaced step could prove fatal. One failed rope could mean disaster. Yet these workers became legendary figures of the project, suspended between earth and sky as they prepared the canyon for one of history's most ambitious construction efforts. By the time the diversion tunnels were completed, attention shifted toward redirecting the river itself. Massive cofferdams were constructed upstream and downstream of the future dam site. These temporary barriers guided the Colorado River into the newly excavated tunnels. Gradually, water abandoned its ancient channel and flowed through pathways created by human hands. For the first time in countless centuries, a section of the riverbed stood exposed. Construction could begin. The dam itself would require unimaginable quantities of concrete. If all the concrete had been poured as a single continuous mass, engineers feared the material might retain heat for decades while curing. Internal temperatures could remain elevated for more than a century, creating stresses capable of weakening the structure. To solve this problem, the dam was built in interlocking blocks. Each block was poured separately. Embedded cooling pipes circulated cold water through the concrete, accelerating heat removal and allowing the material to cure more efficiently. This innovation became one of many engineering breakthroughs associated with the project. Every aspect demanded creative solutions. Every challenge required new thinking. Every milestone expanded the boundaries of what engineers believed possible. As the structure rose higher, its immense scale became increasingly apparent. The dam eventually reached a height of approximately 726 feet, or about 221 meters. At its base, the structure measured roughly 660 feet thick, or about 201 meters thick. Even near the crest, where the dam narrowed significantly, it remained massive. Visitors standing nearby often found their sense of scale distorted. People appeared tiny against the towering wall of concrete. Vehicles resembled toys. The canyon itself seemed transformed. Meanwhile, workers continued labouring around the clock. Concrete pours proceeded day and night. Equipment operated continuously. Crews coordinated thousands of tasks with remarkable precision. The project became a symbol of determination during one of the nation's most difficult economic periods. Newspapers followed its progress closely. Photographs circulated across the country. Americans viewed the dam as proof that large achievements remained possible even amid adversity. Yet success carried a human cost. Construction accidents claimed lives. Heat-related illnesses affected workers. Dangerous conditions were an unavoidable reality of the era. Every milestone reflected not only engineering expertise, but also personal sacrifice. Those sacrifices became woven into the identity of the project itself. When the dam neared completion, its significance extended far beyond the canyon where it stood. It represented technological innovation, economic recovery, national ambition, and confidence in the power of engineering to reshape the environment. Then, at last, the immense structure was finished. The Colorado River, once free to surge through the canyon according to its own rhythms, now encountered a barrier unlike anything nature had ever placed in its path. Water began accumulating behind the newly completed dam. Day after day, the reservoir expanded. Former valleys disappeared beneath rising water. Canyons flooded. Shorelines migrated outward. The transformation unfolded gradually, yet its scale was extraordinary. An entirely new landscape was being born. Behind the dam, a new inland sea began to form. The water rose slowly at first. Week after week, month after month, the Colorado River continued delivering snowmelt and runoff from distant mountains. Instead of racing unimpeded toward the lower basin, those waters now accumulated behind Hoover Dam. Valleys disappeared beneath the expanding reservoir. Ancient river channels vanished under deepening blue water. Cliffs that had once overlooked a winding river suddenly stood above a growing inland sea. As the reservoir filled, it became clear that something extraordinary was taking shape in the desert. The new lake stretched across an immense landscape of drowned canyons and submerged valleys. Shorelines extended for hundreds of miles or hundreds of kilometers. Water occupied places where, only a short time earlier, dry desert terrain had dominated the horizon. The reservoir would become known as Lake Mead, named after Elwood Mead, one of the key figures involved in Western water development. Its size was difficult to comprehend. At full capacity, Lake Mead could store roughly 28 million acre-feet of water, or approximately 34½ cubic kilometers of water, enough to rank among the largest reservoirs in the world. The volume represented years of Colorado River flow held in reserve behind Hoover Dam, creating a level of security that earlier generations could scarcely have imagined. For communities across the Southwest, the reservoir seemed to offer something that had always been elusive: predictability. The river still flowed from the mountains. Snow still melted each spring. Weather still varied from year to year. Yet the reservoir provided a vast buffer between nature's variability and society's growing demands. Floodwaters could be captured. Dry periods could be managed. Water could be released according to human needs rather than seasonal timing. The impact was profound. Cities that once faced uncertainty about future water supplies suddenly possessed a degree of confidence that encouraged expansion. Investors, planners, and developers began looking at the desert with new eyes. Places that had once seemed constrained by the limited water now appeared full of possibility. Few locations embodied this transformation more dramatically than Las Vegas. For much of its early history, Las Vegas remained a relatively modest desert settlement. Its location offered strategic advantages for transportation and commerce, but growth was constrained by the realities of water availability. Lake Mead altered that equation. Reliable access to water supported expanding residential development, commercial activity, and infrastructure construction. Over the following decades, Las Vegas evolved from a small community into one of the fastest-growing metropolitan areas in the United States. Hotels rose from the desert floor. Neighborhoods expanded outward. Roads multiplied. Millions of visitors arrived each year. The city became an international symbol of growth in an environment where such growth might once have seemed impossible. Las Vegas was not alone. Across the Southwest, communities increasingly relied upon the stability provided by Hoover Dam and Lake Mead. In Arizona, California, Nevada and beyond, water stored within the reservoir supported homes, businesses, industries and agriculture. Aqueducts and distribution systems transported water across remarkable distances, connecting distant populations to a resource originating high in the Rocky Mountains. Agriculture experienced a similar transformation. Vast regions of arid land became productive farmland through irrigation. Fields produced vegetables, fruits, forage crops, and numerous other agricultural products that supplied markets throughout North America. The scale of production was extraordinary. Deserts that once supported only sparse vegetation now generated immense economic value. Behind much of that productivity stood a simple reality: water from the Colorado River. The benefits extended beyond agriculture and municipal supplies. Inside Hoover Dam, another powerful engine of development had begun operating: hydroelectric generation. As water passed through turbines deep within the dam, the energy of falling water was converted into electricity. The process produced large quantities of reliable power without requiring the combustion of fuel. Transmission lines carried that electricity across vast distances. Communities received power. Industries expanded. Economic growth accelerated. The dam became more than a water management structure. It became part of the foundation upon which the modern Southwest was built. Generation after generation grew accustomed to its presence. Residents opened faucets expecting water to arrive. Businesses planned around dependable electricity. Farmers counted on irrigation deliveries. Tourists visited a reservoir that appeared permanent. Over time, dependence evolved into familiarity. Familiarity evolved into assumption. Many people never witnessed the Colorado River before Hoover Dam existed. They never experienced the dramatic seasonal fluctuations that had once defined life along the river. For them, Lake Mead was simply part of the landscape, a vast body of water in the desert, a normal feature of the American Southwest, an enduring symbol of engineering success. The reservoir became a destination as well as a utility. Boaters explored flooded canyons, anglers sought fish in deep waters, families gathered along shorelines, marinas expanded to accommodate recreation on a scale few could have imagined when construction first began. From above, the lake often appeared immense and secure. Its blue waters contrasted sharply with the surrounding desert terrain. Its size inspired confidence. Its presence suggested permanence. Decade after decade, the system appeared to function exactly as intended. Water flowed, electricity flowed, cities grew, agriculture expanded. The reservoir stood as evidence that human ingenuity had successfully imposed order upon one of North America's most important rivers. Yet, hidden within that success was a subtle shift in perspective. The generations that built Hoover Dam understood scarcity because they remembered uncertainty. Later generations inherited stability. Many came to view that stability not as an achievement requiring constant management, but as a permanent condition. The reservoir would always be there, the water would always arrive, the system would always function. Such assumptions are understandable. They emerge naturally during long periods of success. Yet history often demonstrates that abundance carries its own risks. The more reliable a resource appears, the easier it becomes to plan around its continued availability. Communities expand, expectations grow, demand increases. Gradually, dependence deepens, and once dependence becomes widespread, even small changes can carry enormous consequences. For decades, Lake Mead symbolized abundance. Its waters fueled growth across the southwest. Its presence encouraged confidence in the future. Its immense storage capacity appeared to provide a safeguard against uncertainty. But an important question lingered quietly beneath the surface. What happens when abundance becomes an expectation? Long before the white mineral ring around Lake Mead became a familiar image, long before declining reservoir levels attracted headlines, and long before engineers began paying close attention to critical elevations, a decision had already shaped the future. It was not a failure of engineering. It was not a failure of construction. It was an assumption. And like many assumptions, it seemed reasonable at the time. During the early decades of the 20th century, leaders from the states connected to the Colorado River faced a complicated challenge. The river crossed enormous distances and served multiple regions with competing interests. Communities upstream worried about protecting their future rights. Communities downstream wanted assurances that water would continue arriving. Without formal agreements, conflict seemed inevitable. The solution emerged through negotiations that eventually produced the Colorado River Compact. Signed in the early 1920s, the agreement attempted to divide the river's waters among the states of the basin. It represented one of the most important water management arrangements in American history. At the time, the objective appeared straightforward. Determine how much water the river could reliably provide. Allocate that water among different regions. Create a framework capable of supporting future development. The challenge lay in the first step: estimating the river's long-term capacity. Today, scientists possess access to extensive records, sophisticated computer models, satellite observations, climate reconstructions, and decades of additional research. The planners of the early 20th century had none of those advantages. Instead, they relied primarily upon the hydrologic records available to them. Those records covered only a relatively brief period of time compared with the immense climatic history of the American West. Unfortunately, the years being measured happened to be unusually favorable. The Colorado River appeared larger than it truly was over the long term. Runoff levels during the observation period suggested a river capable of delivering substantial volumes of water year after year. Based on those measurements, negotiators established allocations that seemed both practical and sustainable. Few people realized that the river had been observed during an unusually wet chapter of its history. The numbers looked dependable. The calculations appeared sound. The future seemed secure. Yet nature operates according to timescales far longer than political agreements. The Colorado River Basin has always experienced dramatic fluctuations. Wet decades can be followed by dry decades. Abundant periods can be interrupted by prolonged scarcity. Tree ring studies conducted many years later would reveal evidence of droughts far more severe than anything recorded during the early years of modern measurement. Those ancient dry periods remained invisible to the planners making decisions in the 1920s. As a result, water rights across the basin gradually became tied to expectations that exceeded what the river could consistently provide over very long periods. The consequences were not immediately apparent. In fact, for decades, the system appeared successful. Hoover Dam was completed. Lake Mead filled. Agricultural production expanded. Cities grew. Water deliveries continued. The Southwest entered an era of remarkable development. Every year that passed without major disruption strengthened confidence in the system. Every successful decade reinforced the belief that the calculations had been correct. Meanwhile, population growth accelerated far beyond what early planners could have imagined. When the Colorado River Compact was signed, the American Southwest contained only a fraction of the population that would eventually depend upon the river. Cities that were once modest communities expanded into major metropolitan areas. New neighborhoods spread across desert valleys, industries multiplied, tourism flourished, demand increased from every direction. Agriculture remained a major consumer of water. Urban areas required growing supplies. Businesses needed reliable infrastructure. Energy systems expanded. The river that once served relatively small populations was now expected to support tens of millions of people. Remarkably, much of this growth occurred because Hoover Dam and Lake Mead appeared capable of making it possible. The reservoir functioned like an enormous savings account. During productive years, water accumulated behind the dam. During dry years, stored water helped compensate for reduced inflows. The system worked so effectively that many people rarely questioned its long-term sustainability. Yet, beneath the surface, a subtle imbalance was developing. Water commitments increasingly reflected expectations formed during unusually favourable hydrologic conditions. Actual river flows did not always cooperate. Some years delivered less water than anticipated. Then other years did the same, and then more years followed. Initially, the reservoir absorbed these fluctuations without attracting widespread concern. That was one of its primary purposes. Large storage capacity provided resilience against variability. But reservoirs are not magical sources of water. They are banks. Water deposited can later be withdrawn. However, withdrawals that consistently exceed deposits eventually create a problem. For many years, the difference remained difficult to see because Lake Mead was so immense. Its vast size concealed gradual changes that might have appeared alarming in a smaller system. The reservoir still looked enormous. The dam still generated electricity. Water still flowed to cities and farms. Life continued much as before. Yet the mathematics governing the system never stopped operating. Every gallon or every 3 8/10 litres released downstream mattered. Every year of below-average inflow mattered. Every increase in demand mattered. The assumptions embedded within earlier agreements became increasingly important as populations expanded and expectations grew. Nature, meanwhile, remained indifferent to those expectations. Snowfall varied. Temperatures fluctuated. Runoff changed. The river continued responding to environmental conditions rather than legal agreements. By the closing decades of the 20th century and the beginning of the 21st, scientists, water managers and engineers began paying closer attention to trends developing across the basin. Questions emerged. Were historical flow estimates too optimistic? Could the river continue meeting all existing commitments? Would future conditions resemble the past? The answers proved increasingly complex. Research expanded understanding of the river's history. Tree ring records extended knowledge far beyond the relatively short period available to early planners. Evidence accumulated showing that the Colorado River Basin had experienced prolonged dry periods lasting decades. Some droughts had persisted far longer than modern society had experienced. Others reduced river flows dramatically. The realization was sobering. The period used to estimate the river's capacity may not have represented normal conditions at all. Instead, it may have reflected an unusually wet chapter within a much longer and more variable climatic record. The implications reach far beyond academic discussions. Entire cities depended upon the river. Major agricultural regions depended upon the river. Power generation depended upon the river. Economic systems worth billions of dollars depended upon the river. The assumptions made decades earlier were now woven into the fabric of modern life across the Southwest. For years, Lake Mead helped conceal the growing tension between expectations and reality. Its enormous storage capacity provided a buffer that masked gradual changes. But no reservoir, regardless of size, can permanently compensate for a mismatch between supply and demand. Eventually, conditions began shifting in ways that were impossible to ignore. The calculations that once seemed reliable started looking less certain. The forecasts became more complicated. The margin for error narrowed. And then nature began rewriting the calculations. For much of the 20th century, Lake Mead seemed almost permanent. Generations grew up with the reservoir as a defining feature of the American Southwest. Travelers crossing the desert encountered an immense expanse of blue water surrounded by rugged mountains and sunlit cliffs. Boaters launched from marinas that appeared securely anchored to the shoreline. Communities throughout the region depended upon water deliveries and hydroelectric power that arrived with remarkable consistency. The reservoir had become so familiar that many people rarely considered how extraordinary it truly was. After all, Lake Mead was not a natural lake. Every drop stored within it depended upon water arriving from far away, from mountain snowfields, seasonal storms, tributaries, and countless streams feeding the Colorado River system. Its apparent permanence relied upon a continuous replenishment cycle stretching across thousands of square miles or thousands of square kilometers. As the 21st century advanced, that cycle began changing. The shifts did not occur overnight. No single year transformed the reservoir. No single season altered the future. Instead, a series of developments gradually accumulated across the basin. Winter snowpacks occasionally arrived thinner than expected. Spring runoff sometimes failed to match historical averages. Certain years delivered less water into Lake Mead than managers had hoped. Then more years followed. Individually, these events appeared manageable. Collectively, they began reshaping the reservoir. Across much of the American West, a prolonged dry period settled over the landscape. Scientists, climatologists, and water managers increasingly described conditions as part of a multi-decade drought affecting large portions of the Colorado River basin. The impacts extended far beyond Lake Mead itself. Mountain watersheds experienced changing runoff patterns. Tributaries delivered reduced flows. Reservoirs throughout the basin faced mounting pressure. At the same time, temperatures across the region trended higher. Warmer conditions influence water systems in numerous ways. Snow can melt earlier. Soil can absorb greater amounts of moisture before runoff reaches rivers. Evaporation can increase from reservoirs, landscapes, and vegetation. The consequences ripple through an entire watershed. Even when snowfall occurs, not all of that water necessarily reaches downstream reservoirs. Some of it returns to the atmosphere. Some is absorbed into increasingly thirsty soils. Some never becomes river flow at all. Scientists studying the basin began identifying these processes as important contributors to declining runoff efficiency. In simple terms, the watershed itself was consuming a larger share of available moisture before it could enter the river system. For Lake Mead, the implications were significant. The reservoir functions like a giant balancing point between inflows and outflows. Water enters from upstream. Water leaves through releases, consumption, evaporation, and power generation operations. When inflows exceed losses, storage increases. When losses exceed inflows, storage declines. Year after year, the balance increasingly favoured decline. The changes became visible. At first, only careful observers noticed. Boat ramps required adjustments. Marinas relocated sections of their facilities. Shorelines migrated farther from locations where water had once reached. Then the evidence became unmistakable. A broad white band emerged along the surrounding cliffs and mountains. Known informally as the bathtub ring, this striking feature marked previous water levels. Minerals left behind by retreating waters created a pale stripe visible from miles away, or kilometres away. As the reservoir dropped, the ring grew wider and more prominent. Visitors arriving at Lake Mead often found themselves staring at this enormous scar across the landscape. It provided a visual measurement of change. The difference between past and present stood literally written upon the canyon walls. Photographs comparing different years became increasingly dramatic. Areas once submerged lay exposed. Old structures emerged from the receding shoreline. Previously inaccessible terrain returned to daylight after decades beneath the water. The reservoir remained enormous by most standards, but its transformation was impossible to ignore. The numbers reflected the same reality. Lake levels periodically reach record lows not seen since the reservoir's early years of filling. Water managers watch forecasts closely. Seasonal runoff projections became major events. Snowpack measurements in the Rocky Mountains attracted growing public attention. Every winter raised new questions. Would snow accumulation be sufficient? Would spring runoff provide relief? Would reservoir levels stabilize? Sometimes conditions improved temporarily. Strong snow years delivered encouraging inflows. Reservoir levels occasionally rose. Optimism returned. Yet the broader trend remained difficult to reverse. The long-term trajectory continued pointing downward. Communities across the basin responded with conservation measures, efficiency improvements, revised operating agreements, and efforts to reduce water consumption. Farmers adopted new technologies. Municipal systems sought greater efficiency. Water managers negotiated complex arrangements designed to preserve storage within major reservoirs. These actions helped slow the decline. They demonstrated that adaptation remained possible. But adaptation could not entirely eliminate the underlying challenge. The Colorado River was delivering less water than many historical expectations had assumed. Meanwhile, millions of people still depended upon the system. Lake Mead increasingly became a symbol of that reality. News helicopters flew over shrinking shorelines. Satellite images circulated widely. Scientists published studies examining changing conditions across the basin. Public awareness grew. Yet even as attention focused on the reservoir's declining volume, many people misunderstood the nature of the threat. The most important concern was not simply the amount of water remaining. Lake Mead still contained vast quantities of water. The reservoir had not disappeared. Boats still crossed its surface. Water still flowed through Hoover Dam. Electricity continued reaching customers. The system remained operational. The deeper concern involved something less obvious, something measured not primarily in volume, but in height. Engineers monitoring Hoover Dam understood that the reservoir served two functions simultaneously. It stored water. It created pressure. Those functions are related, but they are not identical. A reservoir may contain an immense volume of water while still experiencing operational challenges if water levels fall too low. The distinction is subtle. It is also critically important. As Lake Mead continued retreating from its historic highs, attention gradually shifted toward a number that would become increasingly significant. Not the total volume of water, not the total surface area, not the total storage capacity, a specific elevation. Because for Hoover Dam, the greatest danger was not the amount of water remaining. It was the elevation at which that water stood. Deep inside Hoover Dam, hidden behind one of the most recognizable structures in the United States, a carefully orchestrated mechanical world has been operating for generations. Visitors standing atop the dam often focus on the immense reservoir stretching toward the horizon or the towering concrete wall rising from Black Canyon. Yet some of the most important components of the entire system remain largely unseen. Far below the surface, enormous turbines and generators transform the movement of water into electricity. For decades, these machines have quietly helped power communities across the Southwest. Their operation appears almost effortless. Water enters the dam. Electricity emerges. Lights turn on hundreds of miles away or hundreds of kilometers away. Air conditioners cool homes during desert summers. Businesses operate. Cities function. The process seems simple. The reality is a masterpiece of engineering built upon one of the most fundamental principles in physics: gravity. Hoover Dam's power generation system includes 17 commercial generators along with 2 station service generators used to support dam operations. Together, these 19 machines represent the heart of the facility's hydroelectric capability. Each commercial generator is connected to a massive turbine. The turbines resemble giant underwater wheels, although their design is far more sophisticated than traditional water wheels. Water enters through large intake structures positioned high within the reservoir and travels downward through enormous pipes known as penstocks. As the water descends, something important happens. Gravity accelerates it. The higher the water stands above the turbine, the greater the pressure created by the weight of the water column overhead. When the moving water strikes turbine blades, it causes the turbine shaft to rotate. That rotating shaft turns the generator. The generator converts mechanical motion into electrical energy. The concept is elegant. Water falls. The turbine spins. Electricity is produced. For nearly a century, this system has converted the stored energy of Lake Mead into a dependable source of power. Yet a crucial detail is often overlooked. Water alone does not create electricity. Height creates pressure. Pressure creates power. This distinction lies at the center of the growing concern surrounding Lake Mead. Imagine 2 identical containers holding the same amount of water. One is shallow and wide. The other is tall and narrow. Although both contain equal volumes, the pressure near the bottom of the taller container will be greater because the water column extends farther upward. Hydroelectric systems operate according to the same principle. Engineers refer to this vertical distance as hydraulic head. Hydraulic head is one of the most important measurements in hydroelectric generation. It represents the difference in elevation between the water surface and the turbine below. The larger the hydraulic head, the greater the available pressure. The greater the pressure, the more efficiently turbines can generate electricity. Lake Mead functions as an enormous elevated reservoir supplying hydraulic head to Hoover Dam. Every foot, or approximately 30 centimeters, of elevation contributes to the pressure available inside the system. Every foot lost reduces that pressure. At high reservoir levels, water enters the intake structures with tremendous potential energy. Turbines receive strong flows capable of producing substantial electrical output. At lower reservoir levels, conditions begin to change. The water still exists. The reservoir still contains enormous quantities of stored water, but the vertical distance between the surface and the turbines becomes smaller. As hydraulic head declines, generating efficiency declines as well. The turbines can still operate, but they do so under increasingly challenging conditions. This is why engineers pay such close attention to reservoir elevation rather than focusing solely on total storage volume. From a distance, a reservoir may appear large. Its surface may still stretch across miles of desert or kilometers of desert. Millions of acre-feet of water, or billions of cubic meters of water, may remain stored behind the dam. Yet hydroelectric performance depends heavily on where that water is positioned vertically. A gallon of water, or approximately 3 8/10 litres of water, near the top of the reservoir possesses more energy potential than a gallon of water, or approximately 3 8/10 litres of water, located much lower. Elevation matters. The physics is unavoidable. No amount of engineering can repeal gravity. No operating procedure can eliminate the relationship between height and pressure. The entire hydroelectric system depends upon maintaining sufficient hydraulic head. This reality becomes especially important when examining Hoover Dam's role within the regional power grid. The facility does not provide electricity for every community in the southwest. Modern energy systems are far more diverse than they were during the dam's early decades. Natural gas facilities, solar installations, wind farms, geothermal resources, and other generating sources now contribute substantial amounts of power. Nevertheless, Hoover Dam remains an important component of the regional energy network. Its electricity supports millions of people. Its generation can respond rapidly to changing demand. Its output helps stabilize portions of the grid. For decades, the reservoir's elevation remained high enough that hydraulic head rarely attracted widespread public attention. The system simply worked. Water entered the turbines. Generators produced electricity. Communities received power. Few people had reason to think about the precise elevation of Lake Mead. Today, that elevation has become one of the most closely watched numbers in Western water management. Because every foot, or approximately 30 centimetres, matters. Every decline affects hydraulic head. Every reduction influences generating capability. And while Hoover Dam's turbines are remarkably resilient, they cannot operate without sufficient pressure. The relationship is governed not by politics, economics, or public opinion. It is governed by physics. As Lake Mead gradually retreated during recent decades, engineers began paying increasing attention to specific operating thresholds. Certain elevations carried greater significance than others. Above those levels, the system functioned normally. Near those levels, concerns increased. Below them, operational challenges became progressively more serious. The existence of those thresholds transformed reservoir elevation from a technical measurement into a matter of regional importance. A difference measured in feet or centimetres could influence the performance of machines responsible for generating enormous quantities of electricity. And among all the numbers being monitored, one narrow margin was beginning to attract particular attention. A margin so small that it seemed almost impossible. A final band of elevation separating normal operation from a very different reality. What happens when the reservoir loses too much elevation? The answer is both simple and surprising. When Lake Mead drops too low, the dam does not suddenly stop holding water. The concrete structure remains as strong as ever. The reservoir can still contain an enormous amount of water. Water can continue flowing downstream to supply cities, farms, and industries. But hydroelectric generation begins to lose something essential: pressure. Electricity at Hoover Dam depends on hydraulic head, the vertical distance between the surface of Lake Mead and the turbines located deep inside the powerhouse. Gravity pulls water downward through massive steel penstocks, and the weight of that falling water creates the pressure needed to spin the turbines. As the reservoir drops, that pressure steadily decreases. At first, the effects are gradual. The generators continue operating, but they become less efficient. Engineers carefully adjust power production to match the changing conditions. Electricity can still be generated, but every foot of declining water makes the job more difficult. Eventually, however, Lake Mead approaches a critical elevation known as the minimum power pool. This is not the point where the reservoir is empty. Far from it. Millions of acre-feet of water, or billions of cubic meters, can still remain behind Hoover Dam. From the shoreline, the lake can still appear enormous, but the water is no longer high enough. Without sufficient elevation above the turbines, gravity cannot produce enough hydraulic pressure for conventional hydroelectric generation. The generators themselves remain fully functional. The powerhouse remains intact. Nothing has broken. Instead, the laws of physics become the limiting factor. The turbines require pressure. Pressure requires elevation. Without enough hydraulic head, electricity can no longer be generated as Hoover Dam was designed to operate. That is why engineers focus on elevation rather than simply the amount of water remaining inside Lake Mead. The reservoir may still look full to many visitors. Yet, from an engineering perspective, the only measurement that truly matters is how high that water stands above the turbines. Which brings us to an even more important question. How much elevation remains before all 12 generators approach the limits of what physics will allow? The answer is astonishing. The remaining operational margin is measured by just 14 feet, approximately 4.3 meters. 14 feet. That is shorter than many living rooms. It is roughly the height of a single-story building. Compared with a reservoir stretching more than 100 miles, or over 160 kilometers, it seems almost insignificant. Yet those final 14 feet separate continued hydroelectric generation from a threshold engineers have worked for years to avoid crossing. Within that narrow band lies the hydraulic head needed to keep all 12 generators operating. Within that narrow band lies valuable time for heavy snowfall in the Rocky Mountains to replenish the Colorado River. Within that narrow band lies the opportunity for conservation measures, interstate water agreements, and favorable spring runoff to stabilize reservoir levels. Every additional foot of water buys more flexibility. Every foot lost reduces the pressure available to drive the turbines. This explains why Lake Mead has become one of the most closely monitored reservoirs in the world. Engineers track mountain snowpack throughout the winter. They measure runoff forecasts during the spring. They monitor evaporation during the scorching desert summers. They coordinate water releases from upstream reservoirs while balancing the demands of millions of people who depend on the Colorado River every single day. All of those efforts ultimately influence one measurement: elevation. Not because Hoover Dam is in danger of collapsing. It is not. The dam remains one of the strongest and most carefully maintained engineering structures ever built. Its concrete continues to perform exceptionally well after nearly a century of service. The concern is entirely different. It is operational. Can Lake Mead remain high enough for gravity to continue doing the work that powers 12 giant generators? That distinction is critical. If the reservoir were ever to fall below the minimum power pool, the southwest would not suddenly go dark. Modern electrical grids receive power from natural gas plants, solar farms, wind facilities, geothermal resources, and other generating stations connected through an extensive transmission network. Electricity would continue flowing. But one of America's most iconic sources of renewable energy would fall silent. Utilities would need to replace Hoover Dam's electricity with power from other sources, often at a higher cost. Grid operators would lose one of the region's most flexible generating facilities, capable of rapidly adjusting output to match changing demand. The consequences would be significant, even if they were not immediate. That is why engineers continue watching every inch of Lake Mead's elevation. Because the greatest challenge facing Hoover Dam today is not structural failure. It is maintaining enough height above the turbines to keep gravity working in humanity's favour. In the end, the future of Hoover Dam is not determined by how much water remains inside Lake Mead. It is determined by how high that water stands. And today, the difference between 12 generators producing clean hydroelectric power and a silent powerhouse is measured by one remarkably small number. Just 14 feet. Sometimes the future of one of the world's greatest engineering achievements is not decided by massive floods or catastrophic disasters. Sometimes it is decided by the final few feet of water.